Rocks. They existed even before the oceans, forests, and plants came to be, even before the oxygen we breathe. They have been there since the beginning of time and are more than just the solid ground beneath our feet. They are protagonists in the story of Earth and witnesses to its past. Breathtaking rock formations tell of drama and rebirth, catastrophic upheaval and wonder. They are often misunderstood, and yet they are essential because here in this mineral material lies the origin of life.
One of the most extraordinary aspects of Earth history is the coevolution of rocks and life. Life could not have originated without the role of minerals.
Without rocks, there would be no oxygen, no continents, no landscapes, no plants, no animals. For billions of years, minerals and life have depended on one another. This relationship, so fruitful for the planet, developed slowly and steadily, until the day one species began to interfere with the natural order. At first, imperceptibly, then at a rate the Earth had never experienced before.
Humans have always needed minerals from the very beginning. And then the relationship of humans to minerals became more complex.
Within Earth's rock lies the story of life's beginning, the complex structure of the world, and the subtle balance of forces that have always shaped all living things. It is the history of the Earth, our history.
Well, one of the things we know is that a little more than 4.5 billion years ago, our Earth formed. And we know that it formed from materials that had previously been in stars that exploded, putting both minerals, ice, and other kinds of structures into space.
Earth didn't exist, the solar system didn't exist, but there was a vast cloud of dust and gas. The gas was mostly hydrogen and helium that went to make the sun. The dust was literally stardust, tiny particles of minerals that through gravity grew into larger and larger clumps. The size of your fist, the size of a basketball, the size of a room, then tens and hundreds of kilometers across. And as that rocky planet began to grow, all those dust particles became the minerals that would make planet Earth. And so if you think about early Earth, it formed by the accumulation of vast quantities of tiny dust particles, all of them mineral rich, all of them coming from stars, in a very deep and fundamental way. We are all made of stardust.
We are all made of stardust. Everything on Earth is a legacy of the stars. But Earth in its youth looked very different from the blue planet we know today. It was a glowing ball, a molten mass exposed to solar winds and meteorite impacts. Its surface was covered by boiling oceans of magma.
When the Earth was born, it became very hot. And it's generally thought that within 30 or 40 million years of the Earth's accretion, it literally melted.
In geology, we tell the story of Earth through geological eras. The very first is what we call the Hadean, a name inspired by Hades. It was an extremely hot planet with almost no crust, very little solid surface, very little atmosphere, and oceans of magma, a world often described as a mineral hell. It was neither habitable nor hospitable.
In this primeval chaos, a cosmic accident occurred that changed the fate of Earth.
The moon was made, it's almost certain, early in Earth's history, as a planet about the size of Mars collided with the Earth. And as a result of that enormous collision, the debris that was flung out condensed to form the moon, which now orbits around us.
At first, the moon, like the Earth, was a ball of fire. It shone in the sky like a second sun, red hot and molten. The moon's presence would soon start to heavily influence how the Earth would develop, and, billions of years later, create conditions conducive to life. It was the beginning of a great transformation. As the Earth gradually cooled, its elements rearranged themselves. Gravity pulled the heavier materials such as iron and nickel towards the center, where they formed the Earth's core, while the lighter materials formed its mantle. In this unstable equilibrium, the magma solidified on the surface into the dark, compact rock we know as basalt. Basalt became the Earth's first crust. Above the crust, a process just as crucial to Earth's development began. The water cycle started to take shape.
As the atmosphere, which was full of a number of gases, began to cool, one of those gases, water vapor, actually started to condense and rain. And in time, that rain caused us to have bodies of water on Earth's surface, and that was really the beginning of oceans. So in a sense, over its first 100 million years or so, the Earth went from something that was completely alien to something that at least was a little more recognizable as our home. But there was one real difference between that early Earth and the Earth we know today, and that is there was no life.
With its first solid crust and growing oceans, some of Earth's familiar features began to take shape. But volcanoes were still spewing lava flows and gas clouds, filling the atmosphere with carbon dioxide, methane, and ammonia. The water in the oceans of the early Archean era was probably green due to the great amounts of iron. And in this chaos of fire, water, and gas, a momentous chemical process began.
The emergence of life on Earth is still one of the great mysteries. But there's no doubt that the recipe, whatever it was, involved water, involved rocks.
There are several theories. Life could have emerged at the bottom of the oceans, near hydrothermal vents that release very hot water with different chemical conditions. It could also have appeared on the surface of continents in small lakes or hot pools, as Darwin suggested.
Life came into existence due to favorable conditions in which water, heat, and minerals played an essential role. And once it began, it had to find ways to continue.
Well, one of the things that's interesting and that we should always think about is it's one thing for life to form and another thing for it to persist and thrive. For all we know, life may have begun many, many different times on the primitive Earth, but not lasted very long. It simply went extinct. But at some point, life had enough
of failing over and over again, but also enough elements to cross a threshold. And so it happened that one day in the primordial ocean, life forms started to develop, diversify, and gradually adapt. They were made up of simple microorganisms invisible to the naked eye. Some of them began to harness the sun's energy by capturing light, and then producing oxygen, an element that had previously been of no importance.
There was then a major change on the surface of our planet because we went from an atmosphere that contained no oxygen to one that contains a very small amount of oxygen. It almost completely changed the planet, since we went from 0% to 2%. It's a very small increase. We currently have 15%, and we really believe that this was a defining moment in geological history that allowed both the evolution and the diversification of life thereafter throughout the rest of geological history.
The Great Oxygenation Event is this important time when Earth and life are interacting in ways that transform both.
For over 1 billion years, the oxygen produced by the first photosynthetic bacteria was absorbed by the oceans and bound in rock. When these reservoirs were full, the oxygen, which is only moderately soluble in water, accumulated in the atmosphere and gradually changed its composition. Over time, this slowly created the ozone layer, which protected the planet from ultraviolet radiation and enabled more complex life forms to emerge, including early forms of plankton as we know it today. Even now, this microscopic world provides insights into how increasing marine biodiversity changed not just the atmosphere, but also gradually transformed rocks and stones. Marine biologist Colomban de Vargas researches this ecosystem, which continues to be indispensable for keeping the Earth in balance.
What's fascinating is, in 1 litre of seawater, there are between 10 and 100 billion planktonic organisms. That's more than all humans on Earth. Every litre of seawater contains up to 10 times the Earth's population.
Plankton, ancient Greek for wanderer, drifts with the current and today makes up an estimated 98% of marine life. Yet for a long time, it was the subject of little research. In 2009, the foundation Tara Oceans launched a 4-year research project to collect data on these microscopic organisms.
So here it is. This is the fresh plankton we've just collected with a large net. And in this tiny world, which we can't see, that's the magical part, you have very small organisms. There are viruses, which already have quite extravagant shapes, like little spaceships. You have bacteria, which start forming filaments or round shapes that sometimes gather into colonies. Then you have more complex cells, which are my passion, protists. And then there is an entire layer of small animals, many gelatinous creatures, tiny jellyfish, things like that. And all of these organisms interact within a single world that we call an ecosystem. That is really what we need to understand today.
During their expedition, researchers identified more than 250,000 species of plankton, some of which are capable of photosynthesis. In absorbing carbon dioxide in the oceans, plankton has helped balance the atmosphere and has given many cliffs the shape they have today.
Et parmi ce phytoplancton, on a un groupe qui s'appelle les coccolithophores.
Phytoplankton includes a group known as coccolithophores. At some point, these tiny cells learn to produce small calcium plates and attach them to the surface of their cell membranes. This phenomenon is unique in nature. Each of these single-celled organisms forms such calcium plates which look like floating stones. And they have a very important function, because when they die, they sink to the bottom of the sea. Over time, this has created mountains that rise out of the water in some places, such as here in the English Channel. Amazingly, this simple process changed the course of our Earth's history forever.
It is fascinating that many living beings or organisms are capable of forming minerals that remain intact when the organisms die.
As a paleontologist, one very quickly learns that many rocks are made of life, or the remains of life. Many limestones are nothing more than mountains built of skeletons, which have piled up sometimes to kilometers thick.
Only about maybe 10 or 15% of animals, for example, make skeletons that are mineralized, but they have a huge effect on life. They have a huge effect on the Earth itself.
The limestone we see here was formed between 100 and 80 million years ago. This area was once a 300-meter deep sea, a paradise for coccolithophers. Their calcareous skeletons piled up over 20 million years, 2 centimeters every 1,000 years, across the entire plain, forming this landscape. So this used to be the seabed. It was only exposed much later when the channel between England and France was formed. It's amazing that single-celled organisms can create entire mountains. It shows how powerful life is and the influence it has on geology.
For a long time, the primordial ocean was the only habitat for bacteria, single-celled algae, and the first multicellular organisms. The emergence of more complex life forms was just beginning. The conditions for the next evolutionary phase formed in the shallower, light-flooded water zones. Life had not yet reached solid land.
Imagine a time 500 million years ago when there were no plants at all on land. The landscape, the continents would just be barren rock. I mean, that's a geologist's paradise. You could walk around and anywhere you looked, you'd see the raw rock.
So one fact that people perhaps don't often know is that for 90% of the history of the Earth, there's been very little soil covering the surface. And it's only within the last 10% of Earth's history that there's been really deep soils developing. But there's a lot of evidence that there were also huge diversity of microbial species, things from bacteria, fungi, algae, but also things perhaps lichens. Lichens are usually a symbiotic association of an alga and a fungus. And they are remarkable things. They are indeed mini ecosystems. And before the advent of vascular plants, and even after then, they covered vast areas of the terrestrial surface.
Little is known about the age of lichens, as their delicate structure means they leave hardly any fossil traces. But researchers believe they paved the way for life on land. These inconspicuous organisms triggered a huge transformation. By dissolving minerals from rock, they contributed to the early development of biological weathering and started to create soil. This marked the beginning of a new phase as living organisms started to shape the Earth's surface. Even today, lichens continue to work away quietly but consistently, an organism which fascinates biologist Tim Wheeler.
And I worked as a geologist for 20 years on really old rocks, and it was really exciting to tell the story, the history of these rocks. But I just couldn't escape what was growing on the rocks as well. And it was lichens that kind of helped me transition from a geologist to a biologist. This granite, and it's mostly made of silica, which are all these clear, tiny grains in here. But scattered throughout that, I see big, kind of pale off-white grains and a little bit of pink grains. These are feldspars, and the feldspars have high mineral content. They have potassium in them, they can have calcium in them, and it's these nutrients that the lichens will key into to help them grow. It's also mining into the rock, dissolving the crystals, the grains, and then they suck those nutrients back up. And so they're literally cracking it grain by grain. They're opening up this granite. And this is amazing because this is how they physically weather the rock. But another way they do it is a chemical process. And so lichens, you see all these colors often correspond to acids. And these acids, when they excreted from the lichen, they can break down and dissolve the mineral grains. And as they do that, they turn them into clay particles. And then those clay particles could fall out, blow away in the wind or wash away in the next rainstorm. And then those particles start building soil for the rest of the ecosystem to thrive.
Weathering is essentially the first and most important Earth's surface process. Lichens, therefore, are ecosystem engineers, despite the fact that they're small, they're pretty confined to the surface, and they're incredibly slow growing. So in my opinion, and the opinion of many other people, lichens, whilst hugely underestimated, are very important and a fascinating and dynamic part of the history of life on Earth.
When I'm here connected to these rocks, connected to these lichens, I just appreciate knowing that at their scale, at their pace, they're taking all this rock, this massive, this solid thing, and slowly breaking it down into particles. It's so amazing that they're able to do that, but it's a different scale. It's such a slow scale. We're talking millimeters to micron scale, and then hundreds to thousands of years. And it's both, a spatial scale, but also a temporal scale. And it's different than everyday life that we live, humans live in.
By colonizing the bare rock, lichens literally prepared the ground for the first plants on land. But without the moon and its gravitational pull, these plants might never have taken root. For the most part, life emerged out of the water in the unstable zones on flat coasts and in tidal pools.
The tides create environments that are alternately wet and dry. These changing conditions required significant biological adaptation.
So one might speculate that any creature that lives in the intertidal zone has got to get used to being wet some of the time, dry some of the time. And that may well be a factor, if you like, a kind of a helping hand for life.
In these transitional zones, the first water algae, the ancestors of our land plants, began to establish themselves on the mainland. To do that, they had to adapt and develop new protective mechanisms.
Well, if we go back 450 million years ago to the time when land plants were beginning to emerge, at some point there was a population of algae that had secreted some sort of waxy covering on their surface, and that kept them from drying out. That was the first step in the emergence of what would become the forests and woodlands and grasslands around us today.
These first primitive plants provided the conditions for life on land. They formed a waxy layer, the cuticle, which helped them retain valuable moisture. And they had rhizoids, which allowed them to anchor themselves underground. These pioneers laid the foundations for the emergence of root plants, which forever changed the biosphere and the development of ecosystems on Earth.
And this is quite remarkable when you think that many of those plants at the time were really quite small and quite simple. But all plants need nutrients from the minerals within the Earth's surface. So it's very important for them to be able to interact with the surface on which they grow. So those roots establish themselves within the materials, the soils, and transferred those into something really complex. They brought new minerals, they brought a degree of transformation and movement of soils, which just simply wasn't present before then. So it's a very key defining moment when the first land plants arrived and started to sculpt their own habitats.
The evolution of plants on land fundamentally changed our planet, transforming rocky landscapes into green ecosystems. Millions of years later, animals took the same step from water to land. Like the plants that went before them, animals had to adapt to a completely different world. Their bodies were no longer supported by water, the air dried out their skin, and they had to adapt to gravity.
Well, the first thing to think about is that animal life developed in the sea. And so all the different types of animals that we see on land today evolved from aquatic ancestors. And in order to do that, they needed to evolve new structures. So if we think about our own group, the vertebrates, all of the vertebrates that have legs, so-called tetrapods, that live on land, had ancestors that were fish. Now, fish have gills, not lungs. Gills are not very useful on land. So in order for vertebrates to get on land, they had to evolve lungs, which they did. Also, while limbs, when you have fins, those work quite well in the sea, but in order to have limbs that you can actually walk on and be supported by on dry land, you need to have really a reformation of the whole skeletal structure and muscular structure. And again, that takes place.
The interaction of the mineral world with the world of life is probably best seen by the way that skeletons are built and appeared.
Minerals were essential for life to move onto land. Without them, there would be no skeletons or shells. In tetrapods, the change took place inside the body. Their bones, consisting of calcium phosphate and carbonate, became denser to enable them to support their own weight outside of water. Instead of a skeleton, arthropods developed a veritable suit of armor, an organic exoskeleton that protected them from dehydration and predators while also giving them a stable shell. Without these skeletons and armor, the first land animals would not have been able to explore their new habitat and even start to shape it themselves by digging and decomposing the soil.
Burrowing animals are a tremendously important part of the activities of life on Earth, but they're often neglected simply because they're happening under the ground. Like termites, like millipedes, like ants, like spiders, like a whole range of different creatures. So chemically, many burrowing organisms actually ingest or essentially eat the soil. And through doing that, they change the mineral composition. But physically, burrowing animals have huge impacts on the soil because they create a whole series of small and large interconnected pathways and galleries. And that means that the soil can contain more oxygen and water can move more effectively through the soil, leading to a new array of systems within the soil. And that in turn attracts different kinds of organisms and species which can thrive in those new conditions. And we can look back at the history of the Earth and see quite different things happening after the arrival of these arthropods on the terrestrial surface.
The Earth has always been shaped by powerful geological forces: volcanism, plate tectonics, continental drift. But with the emergence of plants and animals, another force, life itself, was added. In tidal zones, certain species, such as sea urchins, still shape and transform rocks and reefs today. For more than 40 years, Michael Russell has been investigating the connection between these creatures and the rock.
I see the interaction with the substrate. I see them grinding away the sandstone. I see the millions of metric tons of sediment that are produced every year. I see a deep history, not just ecologically, but evolutionarily as well.
Sea urchins have populated the oceans for 450 million years. They have an amazing skill. Slowly and persistently, they use their teeth and spines to wear away limestone, influencing the geological dynamics of the seabed.
When a sea urchin settles, it's very, very small. And it has very small spines, it has very small tube feet, and everything is small. But as they grow, they develop a feeding structure. This structure is called Aristotle's lantern. And Aristotle's lantern has 5 teeth. And these teeth are amazing. So they basically are like little rock picks. What they're doing is scraping the rocks when they're feeding. So they're scraping algae with their teeth and they're ingesting it, they're swallowing it. And as those spines are brushing against the surface of the rock, they also are removing some of those sand grains. So it's a combination of the teeth scraping on the surface and the spines brushing against the surface that is, in some ways, very gently wiping away the rock. And as it does so, it's creating this little hole, this little cavity, this little pit. And that process is called bioerosion.
In fact, sea urchins play a much greater role than one might think. As bioeroders, they are part of a geological cycle that is thousands of years old. The sediments they produce are transported away, reach further depths, and then return to the surface, where they shape the seabed and coastlines, contributing to the formation of the continents. It is a slow but influential transformation process.
For me, it's fascinating that these little tiny sea urchins in these pools, in this individual little pit, and you get thousands and thousands of them in these tide pools, are these sculptors. They're the ones that are doing the bioerosion. And over years, over decades, the amount of sculpting, the amount of bioerosion that they create is just, it's mind-blowing.
Animals are incredibly active on and in the Earth's surface, and they're really involved in both creating and eroding the rocks around us. And in many cases, they do this in weird and wonderful ways. And we can divide the ways in which animals cause erosion into two. They can produce physical erosion, or they can produce chemical erosion. And some examples are, for example, that the rock hopper penguins can physically erode many of the surfaces of the rocks on which they nest in parts of the world. And they're also very capable of producing chemical erosion of the rocks through urine and other ways in which they interact with the surface. So animals are really creative and destructive of rocks.
If there were no sea urchins, there wouldn't be the sculptor. It would just be like a block of stone. So the urchins are making those nooks and crannies and crevices. They play a very key role. They're an organism that is so foundational to these systems that I can't imagine these systems without sea urchins.
But sea urchins are just part of a much larger cycle. All over the planet, invisible forces turn rock into dust, blasting, crumbling and grinding it down. Living creatures, but also elements such as wind and water. They all contribute to the slow process of erosion that shapes landscapes and nourishes the oceans. Earth wastes nothing. Rocks that have been loosened from the cliffs and broken down by the tides or by organisms will eventually become rock again. It is an eternal cycle in which every grain of sand carries the history of past worlds within it.
It might feel like the Earth's surface has always been there, which is true from our perspective and within our experience of time. As long as we live, for example, the Alps will exist. But in geological terms, tens of millions of years ago, there was an ocean here. Today, there are mountains 3,000 or 4,000 meters high. And in tens of millions of years, there will be hills or even plains. And elsewhere on Earth, new mountain ranges or new oceans will emerge. It is difficult for us to comprehend that much larger cycles and longer processes have taken place before us and will continue to take place long after us, and that humanity will have no influence on them.
Every mineral grain that's eroded off a mountain tells a story, and that's an epic story. It tells the story of building mountains, of eroding them away, of burying them deeply, but then have a new mountain range take its place. And that is the story of planet Earth. Imagine a rocky outcrop, and rain and wind and ice split off a tiny, tiny fragment. That mineral grain, it gets swept away by the river into a river delta on the bottom of the ocean. The grain may form part, then, of a great wedge of sediments. The pressures are sort of high there, but as it gets buried deeper and deeper and more layers of sediment pile on top, the pressures and temperatures get high enough to change that grain in the rock into a new kind of rock. And it may stay deep on the ocean floor or beneath the surface of Earth for tens of millions of years. But eventually, mountain building happens, those rocks are squeezed, and our original grain goes back up, lifted up by these tectonic forces. And it becomes part of a new mountain range, only to be eroded and weathered away again, go into another river and complete the cycle one more time, and again and again and again over hundreds of millions of years.
The rock cycle has been shaping our planet for billions of years, driven by a triad of water, life, and plate tectonics that, as far as we know, interacts in this way only on Earth. It all begins with magma, which forms rocks, which become the Earth's foundation. Wind and weather cause these rocks to wear down, dissolve, disintegrate into tiny particles, and transform. It is the beginning of a long journey. Rivers carry the particles into the oceans, where they are deposited layer by layer. Over time, they compact into sandstone, limestone, and other sedimentary rocks that form cliffs, plateaus, and seabeds. Under the pressure of the Earth's crust, these rocks metamorphize. Limestone turns into marble, clay into slate. And sometimes an even more spectacular transformation takes place. In the slow dance of the tectonic plates, sedimentary rocks are transported to deeper zones where they melt and turn back into magma, ready to feed the volcanoes and start the eternal cycle all over again. But without water, this cycle would not be possible. Water penetrates deep beneath the Earth's surface, hydrates the oceanic crust, and facilitates the sinking of the plates into the Earth's mantle. This process shapes our world, creates mountains and continents, and supplies the soils and oceans with nutrients. It is indispensable for life on Earth.
This phenomenon has existed since the beginning of Earth's history. Without the rock cycle, Earth would be a different place, and life would cease to evolve. This is exactly what happened on Mars. A very long time ago, at the very beginning, there may have been life there, but it could not survive, because there is no dynamic rock cycle on the surface of Mars.
So the rock cycle and the cycle of life are closely linked. They have been influencing each other for billions of years. It is an ongoing process that goes unnoticed by us and which continues to this day, as can be seen in these dust storms in the Namib Desert in Namibia. Here we witness an amazing journey, one that sedimentologist Roger Swart has been observing for years.
It's great to see these dust plumes because it just shows that the Earth is alive and working well, that it's operational, that these processes are going on.
The Namib Desert serves as both the setting and the protagonist of a phenomenon whose origins lie far away in the mountains. There, rain and wind gradually grind the rock into fine dust. The dust is then carried by ephemeral rivers, which only swell during the rainy season and then dry up again to the dunes of the desert.
The ephemeral rivers just run during the rainy season after big storms. And we'd been flowing very fast, so it was bringing sand down at that stage, but with mud. It gets taken down with the river, and eventually it gets into an area where there are dunes, and the river cannot flow very strongly anymore. It's very difficult for the river to flow strongly through that area, so it loses its capacity to carry sediment, and the muds all settle out in that final sort of phase, the clay deposits.
As soon as the water seeps away, the wind takes over. It swirls up the particles and carries them through the desert. Some of them travel astonishingly long distances.
The mineral is quite platy, so when it gets picked up by the wind, it almost floats in the wind and can be carried many hundreds of kilometers. Wind is really important in helping the clay to move further on and giving it the opportunity to move to the oceans where it gets deposited. The clay particles are important because they contain a lot of minerals within them, including iron, nitrogen, phosphorus in them. So they're important in bringing energy and nutrients to the ocean.
If it weren't for that rock cycle, Earth would become stagnant. It would become dead. Because the rock cycle keeps bringing new nutrients to the surface world. It keeps providing a new store of energy for life to survive. So the rock cycle is a fundamental part of Earth's history, but it's also a fundamental part of our history.
These big dust storms carrying nutrients out into the oceans are important because the oceans are relatively deficient in iron. So they need iron brought in from the continents, and the iron can actually stimulate the microorganisms in the ocean, particularly plankton and algae like diatoms, microbial life, and they're the basis of the food chain that's around us these days.
Minerals were the origin of all life. Gradually, the first organisms began to change their environment. The emergence of hominins in Africa around 7 million years ago marks a key milestone. Our ancestors were primarily tree dwellers and fed on leaves and fruits. But at some point, they left the treetops and stepped onto solid ground. Their first steps were more than just a new form of movement. They marked the beginning of a unique relationship with rock.
For most of our ancestral history, we're four-legged creatures, walking around on all fours, perhaps aided by the fact that we used to hang in our arboreal existence by our forelegs. Every now and then we would lean back on our hind legs to look above the savanna grasses, see where potential predators might be or potential prey. And then we're back down to move on our all fours. But at some point, we got so skilled at balancing on our hind legs that we even began taking a step to one side or to another side, and even began walking around just balanced on our hind legs. that freed up our hands in a whole new way, and our exquisite opposable thumbs to engage, to manipulate, to take up, to begin to play with the mineral structure of the world and to fashion things and make things. Tools.
Imagine that first primate taking a stone in its hand and realizing you could do something new with it. It may not have been a conscious thought in the mind of the earliest primates to use stones, but it just became an instinctive extension of your hand, something that gave your hand more heft, more weight. It was a tool you could use to survive. I like to think that invention is an important part of the evolution of primates and of humans. If you learn to do something new, if it allows you to live your life more efficiently, more safely, if it allows you to defeat your enemies, to hunt prey, any of these things that rocks can allow you to do becomes an advantage. And I think that's how evolution of primates were co-evolved with rocks.
From walking upright to using tools to discovering fire, minerals have always been our silent allies, the foundation of human development. For millions of years, our ancestors explored the world, observing and experimenting. At first, they used unworked stones. Later, they selected specific ones and worked them into simple tools. Gradually, the tools became more and more sophisticated. This marked the beginning of the Stone Age. Another decisive step was the use of fire, which can be traced back to around 1.5 million years ago. These skills changed the relationship between early humans and the world as they developed new strategies to secure their existence.
Human use of fire, or human domestication of fire, is very much related to rocks, as one early way of starting fires is to rub two rocks together. And I think that shows very nicely the interrelationship, the necessity of the rock and the mineral world for humans.
Flint and pyrite are usually used to produce sparks. The sparks land on a soft mushroom, for example, and then start to burn. Once you're ready, blow on it with a little air. And then one can start a fire relatively easily with fine grasses.
Und dann mit feinen Gräser kann man ein Feuer relativ leicht herstellen.
The development of fire use brought about far-reaching changes for humans and for human history.
We know that the use of fire made it possible to cook food, and because we were able to cook food, you could ingest the calories much more efficiently. And therefore, there are some anthropologists who actually argue that the size of the brain was able to increase. In other words, our symbolic capacities, our ability to think and to reason, and perhaps even speech itself, could emerge from our connection to this process. So I think you can argue that in many ways you begin to see the foundations of more complex civilizations, communication, organizations, and then all the other benefits, of course, that fire can bring to human beings, for safety, for light.
The warmth and light of fire turned caves into places of refuge, places where people gathered and began to tell each other stories. In the flickering glow of the flames, gestures were repeated, tools were perfected, and knowledge was passed on. An ever closer cultural bond developed. Much later, these same rock walls became the canvas for the first cave paintings. Carved, blown, or drawn, they bear witness to the beginnings of human art. These rudimentary figures and animal forms reveal early attempts to depict the world and preserve memories.
When I stand in front of this wall, I feel like I'm looking at a book left behind by our ancestors.
Various ethnic groups have lived in southern Africa for more than 40,000 years. The traditional hunters and gatherers uniquely understand how to read the landscape. Thanks to their ancestors who immortalized their knowledge on the rocks.
The rock tells me how my ancestors lived, what animals they hunted, and how they used them. They fed on their meat, kept warm with their skins and hides, and made tools from their bones. Large animals indicate potential danger. Antelopes and springboks reveal that there is food in the area. The rock tells me all this. It's almost as if they left messages and clues for future generations on this wall. My ancestors couldn't write, but they could paint on the rock. That's how I know where I come from.
Rocks are so much alive. They have witnessed all the changes that human cultures and human history has gone through.
Since the very first cave paintings, rock has been a conveyor of thoughts, a medium of memory and tradition. People immortalized their first beliefs, stories, and worldviews on stone. Millennia later, Neolithic peoples continued this special relationship with stone. This time, it was not only the cave walls that bore their traces, the landscape itself became a sacred site. For example, in Carnac, France, where huge stone blocks were erected and arranged in rows. It was as if, after drawing on stone for so long, humans now wanted to shape the world out of stone. To this day, researchers are trying to solve the mystery of these stones. One of them is archaeologist Philippe Guezin.
Sometimes I just sit down and look at the stones. I try to understand them I'm drawn to them. I feel comfortable here.
C'est une contemplation, un bien-être.
In Karnak, more than 3,000 menhirs are lined up over several kilometers, forming one of the largest megalithic sites in the world. The Neolithic builders probably chose these stones for their durability. They wanted to leave something lasting behind, something that must serve a specific purpose.
Walking among these monoliths, one wonders what they mean. Are they an expression of territoriality, of power, of permanence, of immortality? There are many unanswered questions. Unfortunately, there are no inscriptions, only a few engravings, some schematic, some symbolic, some completely incomprehensible. That is perhaps the most difficult part, identifying how much symbolism is hidden in this stone ensemble.
Humans have an almost sacred relationship with the mineral world. And I think the reason has to do with time. Our lives are so short. We think in terms of days and weeks, months and years. But the rocks, the minerals, they last for millennia. They last for millions of years. And so when we build our sacred monuments, these are symbols of eternity because the time spans of rocks and minerals are so vastly greater than anything we know.
Their beauty and durability have given the stones something sacred. It is an ancient belief that stones protect us from disasters or connect us to a higher power.
During the Neolithic Revolution, humanity laid the foundation for its domination of the world. Hunters and gatherers settled as farmers who altered the natural landscape. Meadows and fields appeared. Villages were built, roads were laid. The development of metallurgy around 5000 BC changed everything. Humans were no longer content with raw rock. They began to mine mineral ores and extract valuable raw materials from them. Copper, bronze, and iron revolutionized societies. At the end of the 18th century, something happened that stepped up this trend: the Industrial Revolution. Instead of simply processing the mined minerals, now energy was to be extracted from them. Coal and later oil formed the cornerstones of this revolution and catapulted society into the age of unbridled consumption. Within a few centuries, our relationship with rock has changed radically. It all began with one worked stone. Today we graze the earth and consume it. We have evolved into an extractivist society in which the earth's resources are being exploited at a murderous pace to satisfy our material and energy needs.
With extractivism, you're
mining, you're removing, you're extracting a resource that is inherently limited. And you're doing this because it is the basis of your society, of both your power, but also a multitude of other things. Your luxury, your ability to move, the things you enjoy in terms of electric lights, of automobiles, plumbing, all of these come from this extractivist societies. And this has all sorts of consequences for the shape of the planet, for the morphology of the planet.
Humans are altering the carbon cycle of our planet in ways that will resonate for thousands and thousands of years. You can't just remove hundreds of millions of years of dead plant material that has been sequestered underground, take it to the surface, burn it, and expect that things will be the same. Will cause global warming, also much more violent weather events, hurricanes and tornadoes, storms. It'll cause drought in some areas, but it'll cause flooding in other areas. When you change the environment, you change how Earth reacts. And it's only going to get worse unless we change the way we think about our relationship to Earth.
Humanity has become a geological force in its own right, shaping a new geological epoch, the Anthropocene. For the first time in the history of Earth, societies are interfering deeply with natural cycles, thereby changing the climate, erosion, the chemistry of the oceans, and even the structure of rocks. But we are not only depleting Earth's natural resources in record time, we're also producing new materials that accumulate in geological strata. Concrete is the best example of this. It is made from lime, clay, and sand heated to high temperatures. Concrete is the artificial building block of our civilization and covers the entire world.
It's much more efficient, it's much more smooth, it offers much less resistance to walk on concrete than it does to walk on earthly ground and to navigate among stones and larger rocks and clumps of grass. What the earth asks of us is to improvise at every moment, to be really wakeful and aware and creative. But we do away with the need for any such creativity when we create a world that is made all of slick surfaces.
Humans in the last 70 years have made more than 500 billion tons of concrete. And that is equivalent to a kilogram of concrete for every square meter of the earth, land and sea. The main ingredients of a concrete, that sand and those pebbles, are made of very hard-wearing minerals we know have lasted for hundreds of millions and even billions of years.
Imagine if all human life disappears. Our cities are empty. The highways are empty. The skies, no more jets flying around. We will leave behind a very distinctive mineralogical legacy.
In this new geological layer, the subsoil would be completely transformed. The ubiquitous concrete would form huge sealed surfaces studded with steel, glass, new types of alloys, industrial ceramics, and semiconductors. However, the real geological signature of our era would be plastic. From things we have used and then thrown away, to nanoplastics that are invisible to the naked eye. Plastic waste is everywhere. These tiny plastic particles are already polluting ecosystems. They're in the soil, in the oceans, even in our rain. In some places, they even fuse with natural sediments under the influence of heat. These hybrid structures have a name: plastiglomerate. João Canning, founder of the Mare Madeira Research Institute, is investigating this phenomenon.
I think the plastic crusts, not only in Madeira but in the world, is telling us something. I think it's a symptom of today's era. It's a sign of alert, that all of us need to be alert.
This global phenomenon shows how deeply our footprint is etched into the earth forever. Plastiglomerate was first discovered in Madeira in 2016 and can now be found worldwide, in the Mediterranean, Peru, Brazil, and Japan. Currents, storms, and waves wash the plastic particles onto all of the world's coasts, where they bind with the rocks.
The first factors is the mechanical action of waves throwing bigger items of plastic towards the rocks. Second, we think that these rocks, they need to have a peculiar, a specific texture. And third, these rocks, they need to be very hot. Because when you look at these plastic crusts, you can see that they kind of melted and they kind of glued to this texture of the rocks. And now we know that the surface of these rocks in certain times of the year, mainly summer, they can reach over 60 degrees Celsius, which is very, very hot. So we think it's a combination of these three things: mechanical action, temperature, and texture of the rocks.
Microplastics to become so omnipresent in our environment that these plastics, whether it's a bag or it's a children's toy, get ground down and they enter into the ecosystem through the oceans or through tidal action and waves that then are ingested by sea creatures. And oftentimes when humans eat those sea creatures, they end up in our own bodies. So here's yet another way where the material world, the mineral world, is in some sense colonizing human beings. We know that many plastics are carcinogens, that they have chemical effects, that they're endocrine disruptors, that they can change our hormonal levels. But honestly, we have no good grasp of that yet. So it's part of this great big experiment that we're running on ourselves, in which we're the guinea pigs, and we really don't quite know what the consequences of this will be.
Plastiglomerate represents the aggressive intervention of the profit-driven petrochemical industry in the rock cycle and how it leaves its mark deep in the Earth's crust. The rocks that were once formed from cooled lava or deposited sediments are now being shaped by our waste. For a long time, it was thought that a world of plastic and concrete would elevate us above nature. Instead, we've etched our presence, rather questionably, deep into its foundations.
Some people may say that our modern technological society has elevated us above previous societies, previous races, the primitive that used stone tools. But in a sense, we're really no different, are we? We still depend on the rocks, the minerals. Every bit of our technological society depends on geology.
Just in this room where I'm sitting right now, I am surrounded by a variety of minerals that would have been impossible 100 years ago to bring into one room. I'm sure there's lithium in the batteries of these cameras. I know that there's copper in the walls around me. There's aluminum in the chair that I'm sitting on. There's probably rare earths in the computers and the cameras that are recording this as I speak. All of these things, they come from all around the world, many of them from relatively isolated mines. It's a wonderful technological innovation, but it's also goes to the point that we're deeply embedded into this material world, more than we ever had. Science is verifying, telling us that there was a deeper truth in that kind of respect that earlier human beings had for the world around them, for the mineral world. So to think of minerals more in an animistic way, to see them and recognize the way that they really have a certain life and are instrumental to our own life and the properties of life all across the planet, I think is absolutely essential, and we need to get back to that way of thinking.
The Earth carries its history within itself. Long before our time, it experienced hot and cold ages and saw oceans and continents emerge. Over billions of years, geological forces have shaped the face of the Earth. Every rock, every mountain, every valley is the result of an infinitely slow transformation process that has been deeply inscribed into the rock. And then, a second ago in historical terms, something changed. A radically new development has disrupted a model that has evolved over billions of years, destabilizing the Earth's geological balance at an unprecedented rate. Within just a few centuries, humanity has extracted the legacy of earlier ages from the ground, and now, in record time, we are burning what the Earth has fossilized over millions of years. We are covering the planet with plastic, concrete, and alloys, thereby creating our own geological layer that marks our era as a brutal anomaly in the history of Earth. But if the Anthropocene is the age of humans, it also has the potential to become the age of awareness. Since Homo habilis made tools out of stones, humanity has been closely connected to the rock that ensured its survival and was the building material for its civilizations. Many of today's societies have grown up in a world of abundance. They find it difficult to think about scarcity and to do anything but exploit. The Earth is telling us the story of its plight. We just have to listen. Those who are already doing so know that it is almost too late.
Earth whispers to us, and yet at times we struggle to hear the message. Here, I think the problem is not so much how loud Earth whispers, but how slowly. The sentences with which Earth speaks to us take millions of years. And so we have to slow ourselves down We have to listen carefully. Listen to the stories the rocks are desperately trying to tell us.